Well, good day everybody. My name is Rob Brown. I'm the engineering trainer here at Allied, and we're here to talk to you today about our Vortex TA Pro and a variety of different Wohlhaupter tools. We're going to use our 248 design, which is designed for long reach, and we're also going to use our prime bore tool, which is a good versatile multi-use tool for job shop environments. So I want to start off by talking a little bit about the tools we're going to be using today, and then we're going to talk about the materials and the machine and all that kind of fun stuff. But we're going to start off talking about the Vortex drill because that's the first thing you're going to see whenever we run the demos. The Vortex is Allied's IC drill offering. The diameter range on it is from 12 to 47 millimeters, which in inches is about a half an inch up to just about inch and 7/8. And the way the Vortex works is that you have two different inserts that are doing the cutting. You have an inboard insert and an outboard insert, one for cutting the center of the tool, the other for doing the periphery work. And the unique thing about the Vortex design is it uses the same insert in both pockets. It's just the orientation of the tools. So to look at it underneath the camera here, so you can kind of take a look at what's going on, you can see here's the Vortex insert right here for doing the center work, and you can see the way that it's orientated is to use this cutting edge here, because I'm trying not to wave around too much. And then here's the insert for the other side, and you can see that it is, if we can get it to focus there it goes, that it's going to do, it's rolled over on its side, and it can do work going in the other direction. So what this allows us to do is I'm going to use this insert or this orientation for cutting on the periphery, because this is where my positive cutting geometry is. And whenever we do the center cut, we lay it on its side, and this geometry here is for strength, to give you the strength you need at the center of the tool. The geometry of the insert of the tool is the flutes are asymmetrical. So what that means is that we have a slightly larger flute for the center of the tool than we do on the periphery of the tool. And that's because the chip's going to be larger on the center than it is on the periphery, which we'll show you that whenever we run the tools. We have 5 different inserts available, and they're based on ISO classifications. We have P for steel, K for cast iron, N for aluminum, H for hardened steels, and then M and S for stainlesses and high temps. The one we're going to be using today is the M geometry, which is for stainlesses and high temps, because that's what we're going to be running today. So we're going to follow that tool up with our Wohlhaupter 249 boring head, or 248. The 248 is metric size, 249 is inch, if I remember correctly. And basically what this tool is designed for is to be able to reach down into pockets and whatnot in order to be able to do the bore, because the boring head is nice and compact, so that way it's made to get down past fixturing or odd shaped parts or something like that. The tool uses a vernier scale, which we'll kind of take a look at it underneath here. Okay, and you can see the vernier scale right here. The graduations on this, now this one is an inch, so this is a 249 head, and the graduations are in 5/10,000ths of an inch increments. So that means the accuracy of this is within 5/10. So we'll be running that after we run the Vortex drill. And then the next demo, or the next couple of demos we're going to use TA Pro as the drill, and then we're going to run the prime bore for the secondary operation that we do in the first cut. So the TA Pro is our latest offering from a high performance drill standpoint, and what it has is ISO specific geometries in the front. We have 4 of them that are available. We have P for steel, K for cast iron, N for aluminum applications, and then we have our new M geometry for stainlesses and high temps, which once again is what we're going to be using today based on the materials that we're going to be cutting. We also have an X geometry, which is not an ISO standard, but it is for, it's a stainless steel geometry that allows you to run in applications where maybe the rigidity is not there for a carbide application. Just taking a look at this one real quick underneath the camera, you can see that the geometry of it, it uses, get my little pointer here, it uses Allied's notch point geometry in the front. It has a parallel cutting geometry for giving you good chip formation and materials, in this example, like high temps and stainlesses. And you can see, since this is the M geometry, it has these little slits in the margin of the tool which aids in the usefulness of the tool and gives it longer tool life and allows you to run higher speeds. The holder that it's in is a redesigned version of our TA holder. It has increased coolant holes and a larger flute. The flute design allows for better chip evacuation, and then of course by having larger coolant holes we're going to get more coolant at the same pressure, and with this design it gives you about 25% more coolant at the same pressure compared to the original TA design. And anytime we're talking about doing successful drilling, I got to do two things. I got to form the chip and I got to get it out of the hole. The geometry allows us to get good chip formation, and the flute design and the coolant design of the holder allows us to evacuate those chips once they're formed. All right, so the last tool that we're going to be using is the prime bore tool from Wohlhaupter. And the prime bore is a versatile boring tool where I can have this one body and I can do a large range of sizes from very small diameters up to about 8-inch diameter, so it's got a nice wide range. In this tool, as we look at it underneath here, it uses a vernier scale for the adjustment on it. And so these graduations, I'll use my little pointer again, these graduations here are in 5/10 increments, and then this vernier scale allows us to have 1/10 setting capability, so it has a much tighter tolerance than the 248 or 249 head that we talked about just a second ago. These tools, or the prime bore tool, is available in a kit form, which is what this is here. Kind of show that to you, and you can see you get the prime bore tool plus a variety of different heads to be able to do a wide variety of different diameters with that one tool. So it gives you good versatility. It is a lower cost option for this versatile style tool because Wohlhaupter does make varying different types. There's a prime bore, a variable bore, and digibore, and the variable bore and the digibore give you the capability to use a digital readout, where the prime bore is vernier scale only. So those are the tools we're going to be using today. So let's tell you a little bit about the machine, and we'll kind of describe to you what applications we're going to be running today, and then we'll show the tools in action. So the machine we're running on today is a Kitamura 30 horsepower machine that has the capability of doing up to about 1,000 PSI, which is about 70 bar. We're going to have it set at a more normal number. Most of the applications we're going to be running are going to be set at 300 PSI, which is about 21 bar. Or for the deep hole application we're going to run today, it's going to be set at 600 PSI, which equates to about 41.5 bar. So the applications we're going to be running today are in materials that are a little different for what we normally show. A lot of times we'll run in an alloy steel and aluminum and cast iron and more common materials like that. What we're going to be running today are more exotic materials. We're going to run a titanium 6AL4V application, and then we're going to run a couple of applications in 718 Inconel. So it'll kind of show the capabilities of these tools in a more unique or a more exotic, difficult to machine environment. So the first application we're going to run today is a 16 millimeter diameter Vortex, which is 629.9 or about 630 thou diameter, going about 1.5 inches deep, which equates to just under 40 millimeters in depth. We're going to run at a speed of 150 surface feet and 2.5 thou per rev, which in metric is 46 meters a minute and 0.06 millimeters per rev. So that's what we're going to do with the Vortex, and then we'll come in with that 249 head, and then we'll finish the hole, and we'll take a look at the hole size, give you a peek at the quality of the finish. We'll also gather up some chips and take a look at those as we go. So once again, this is running the Vortex drill using the M geometry inserts at a 16 millimeter diameter, running 150 surface feet, 2.5 thou per rev, in 6AL4V titanium. That's roughly about 30-ish Rockwell, maybe a little bit harder than that, but it's in that ballpark. So as you can hear, the tool is nice and quiet when it's running. The load meter is running a nice steady 7% as it's going through there. And once again, the coolant is set at 300 PSI, which is about 21 bar. So as you notice, it's not exactly, it's not running super fast through this material, but when you're talking about exotics and high temps, a lot of times the speed and feed that the tool runs is going to be reduced based on the inability of the material to absorb heat. So to trying to cut down on the amount of heat that gets generated, you're going to run lower speeds and feeds in order to do it. So we are just about through the hole, and it should be done now. So we'll gather up some chips and take a look at them, and then while we're looking at those, Dave can get us the part out of the machine so we can take a look at that. Yeah, that's right, we do have to bore it. Good thing Dave's on his game today because I missed that part. But the Vortex, one of the advantages of the Vortex drill is the consistency of the life of the tool as well as the quality of the chip formation that it creates. So I'm going to show you these chips, and I'm going to, there's one right there. So let me grab. You got a center as well, cool. So let's take a look at the chips that we got here, and we can show you what the differences look like. If I can try to get this in a nice spot for you here. So this chip, let me get my little pointer out here and show it to you. This chip right here is the chip that comes out of the center of the tool. Okay, because remember the geometry of the application, at the center of the tool I need strength, I don't need chip formation because of the zero surface footage at the center of the drill. So the fact that we're making a longer chip is not an unexpected outcome, but remember the design of the tool does allow us to do that because of those asymmetrical flutes. This is what the periphery makes here. So you can see these chips here are what we get with the periphery of the tool, and you can see it made a nice tight chip formation, which is really, really good. So we're quite happy with that. So what we're going to do for the second part of this application is we're going to come in with a 248 boring head. So this would be a metric version, but it's the same tool that I showed you just a moment ago. The diameter is set to 650 thousandths of an inch, which is 16.5 millimeters in diameter. The depth of cut that we're going to do is going to be 10 thou or 0.25 millimeters, running 150 surface feet and 2 thou per rev, which is 46 meters a minute, 0.5 millimeters per rev. And this is using a 199 geometry and a WHC 114 coating and substrate for the insert. This particular tool has a triangle insert in it. It's a F20, so it's a triangular shape. But let's take a look at this, or I'm sorry, this is an F101, so this is an 80-degree diamond. It says there it's an F101. So let's take a look at what we got going on here. Let's go ahead and run it. And then we will take the part out of the machine, take a look at it, and we'll gauge it for size because it should be 650 thou in diameter, 16.51 millimeters. Once again, we're running 150 surface feet and 2 thou per rev, which is 46 meters a minute, 0.51 millimeters per rev. And the depth of cut that we're taking is 10 thou or 0.25 millimeters. So we're opening up the hole from 630 thou to 650. So this is running once again in 6AL4V that's somewhere in the low 30s in Rockwell in hardness. And we're still running the coolant at 300 PSI or 21 bar. And this tool does have coolant through capabilities. So once we get the hole done here, this is also going to be going about 1.5 inches deep. And the load is inconsequential because we're taking such a small cut, but it's running what looks like about 4% spindle load, and we should be about done. So we'll take the part out of the machine here and take a look at it, gauge it for size, and see how it works for us there. So once Dave gets that, we'll go from there. We don't gather up the chips for the Wohlhaupter tool because they're very small chips, so there's not really much to see there anyway. Chip formation, while it's very important and boring, isn't as critical as it is in a drilling application. So let's take a look at what we got here. Grab a napkin. And once again, we're going to gauge this hole for size. And we'll show you the finish underneath the camera there. I'm on your left side there, Dave.
It's the hole on your left.
Okay. What was that again?
On your left.
On my left. Okay, thank you. All right, so let's take a look at what we got here. So this is the quality of the hole. You can see it came out really nicely. Given it the whatnot there, I would say that that's probably about roughly about a 30 finish, somewhere in that neighborhood. And you know what? I don't have a gauge for measuring the size on this one. So that's what we've got going on in 6AL4V titanium. So that's what we got there. So we're going to move on to Demo 2. Demo 2 is going to be using a TA Pro for the initial drilling, and then we're going to come in with a prime bore afterwards. So the diameter of the TA Pro is inch 228 or 31.2 millimeters in diameter. The depth of cut is going to be inch and an eighth because this piece of 718 Inconel is inch and an eighth thick, which is about 28.5, 28.6 millimeters depth of cut. Speed that the tool is going to run is 110 surface feet a minute, 8 thou per rev with the TA Pro M geometry, which equates to 34 meters a minute, 0.2 millimeters per rev. Once again, I have the coolant set at 300 psi or about 21 bar, and we're going to drill the hole. We'll take a look at the chips, but once again, we're going to have to wait until after we get the boring work done to take a look at the quality of the hole. So once again, this is using a number 2 series TA Pro M geometry in 718 Inconel, and I believe it's about 170 Bernal in hardness. Coolant at 300 psi or about 21 bar. So we're going to start the cut now. And what we're going to do is the tool is going to make a little bit of noise as it runs. You know, this is a material that's relatively difficult to get to behave the way that we want it to. But this is 718 Inconel that's about, like I said, about 170 Bernal in hardness. We're running 110 surface feet a minute, 8 thou per rev, which is 34 meters a minute, 0.2 millimeters per revolution. Okay? So let's gather up a couple of chips and take a look at them while Dave gets ready to run the prime bore tool. Take a look at some of these chips. And remember, the geometry makes a decent chip, and then the holder design does a good job of getting the chips out. The larger flutes allow for more chips to flow. And then on top of that, we have more coolant available to us. Remember, about 25% more coolant than what we would get with a regular TA body. So that's a really nice improvement to have. And you can see the chip form that we get is nice and small. And for Inconel, this is actually pretty well formed chips. So they look pretty good. So now what we're going to do is we're going to go into that same hole, and we're going to open it up from inch and an eighth diameter up to what are we going to here? Inch and a quarter. So we're going to take a depth of cut of about 11 thou or 0.28 millimeters depth of cut. The speed and feed this tool is going to run is 150 surface feet a minute, 2 thou per rev. Feed rate, which is 46 meters a minute or 0.05 millimeters per revolution. And we're going to have a finished hole size in metric that's 31.75 millimeters in diameter. So we're going to be using the prime bore tool with a boring bar in it, using an F20 insert that's a 121 geometry, a WHC 111 substrate and coating. So we're going to start making the cut here. Go ahead, Dave. And once again, this is in 718 Inconel that's about 170 Bernal in hardness, still running 300 psi of coolant, which is 21 bar roughly. And we're going to open this hole up to an inch and a quarter diameter. Once we get done with this, we'll check the hole size, try to get a visual on what the finish looks like, and see how this tool did. So as you know, this material is extremely difficult to get any kind of good tool life or anything like that. So it does create a situation where the speed and feed that the tool is running is relatively slow based on the fact that this material is a high temp alloy. So all the heat's basically staying in the tool. So it makes a situation where we've got to reduce our speeds and feeds accordingly. So once we get through this, which we've got about another 1/4 of an inch-ish to go in depth before we're done drilling this, then we'll pop it out of there and take a look at it and see what's going on. And we've got about now we just finished up, so there we go. So once again, we're going to get the part out of the machine, take a look at it, see what's going on there. We've got to give Dave a minute to get that thing out of there. And then we're going to go to another demo. So the geometry and substrate that we use for the Wohlhaupter tool is something that is designed to be used in high temp applications. If you're not sure what insert to use, you can always go to Allied's website. We do have a boring insert selector that's available on our website that you can go in and enter in the material that you want to do, whether you're doing a finishing operation or a roughing operation, what insert shape that you need to have, what corner radius you want, and then it'll recommend an insert for you. Greatly reduces the going through the catalog, looking at the several different types that we have to be able to get a good idea for what's going to be the right one for your application. Let me dry this off a little bit so you can see a little better here. We'll show this to you first off. So here's the quality of the bore. Okay, it actually came out quite nice, as you can see. So it looks pretty good. Okay, so let's see if we can get the gauge on here and actually see what the gauge reads. Get this on here. Okay. Let me see if I can tilt this so you can see it. Hang on here. There we go. There he is. So it was set for 1.250, and it was there until it bumped down. It's 50 millionths undersized, so it's not really true. It actually is on size. So the tool did exactly what we wanted it to do. It cut 1.250. So we got a good quality outcome with the tool. Everything works really well there. Now I gotta give this part back to Dave so we can put it in the machine for the next demo. So the prime bore tool, once again, it does a great job. It's a good tool. The reason it's at the point of being like a job shop versatile tool is because you can get the kits and you can do a wide variety of different sizes. And it is a lower cost tool because it is a vernier scale instead of a digital scale, which allows you to do things at a lower cost than if you had a digital readout. So if you're comfortable using a vernier scale, it's a great tool. It works exactly as advertised, which is what you want to see. So while Dave's getting ready here, let's go ahead and talk about our last demo today, which is going to be using a TA Pro geometry tool to do a deep hole drilling application in 718 Inconel. So what we did is that coupon that I just showed you the finish on for the 1.25" diameter, we're going to flip it up on its side and drill a hole through the side of it. So we're going to go a total of about 5 inches deep, if I remember correctly. I'm pretty sure that's where we're going. And we're going to do this in 2 operations because this is going to require a longer length tool, so we're going to follow Allied's deep hole drilling guidelines. And so we're going to come in with a pilot drill, establish the hole, and come in with a longer tool, and we'll talk more about the deep hole drilling guidelines in a moment. But let me tell you what tools we're going to be using here. So we're going to use a number 1 series TA. The body is going to be a B diameter. With the TA Pro bodies, we have different sub-series within a series, so that way you can maximize the rigidity of the application based on the diameter that you're going to cut. So this is a B size, so it's the second smallest size. The diameter we're going to be cutting is a 20 millimeter diameter, which is 7/87 an inch. The depth of cut we're going to do with the first cut is a 2-inch deep hole. This is going to establish the hole for that deep hole drilling guideline, which is about 50.8 millimeters deep. We're going to be running a speed of 88 surface feet and 4 thou per rev, which is 27 meters a minute or 0.1 millimeters per revolution. We're going to change the coolant pressure from 300 psi or about 21 bar up to 600 psi or about 41.5 bar. The reason we're going to do this is now that the chips have further that they need to travel to get out of the hole, we want to make sure we've got a sufficient amount of coolant movement, kinetic energy to keep that chip moving. So that's why we're going to do that. The insert we're going to be using is one of our M Geometry TA Pro inserts that is a 20 millimeter diameter. So before we get started on doing the actual cut, let's talk about the deep hole drilling guidelines. Since we're going to be using this longer tool, anything 9 times D or over to Allied is considered a deep hole drilling application. And what we want you to do is we want you to run that short link drill like what we're going to run here to establish the hole. That does 2 things for us. It actually gives you the best starting condition with the hole on its own, because the shorter drill is going to move around less, so you're going to have better positioning, less taper, a more true hole size. The other thing that does for us is it basically turns our workpiece into a bushing that helps stabilize that longer tool when it goes down to do its cut. So we're going to drill the short hole first, and we're going to come in with the long tool. When we get down in there, we're going to run that longer tool at about 50 RPM until it gets about an 1/8 inch or about 3 millimeters from the bottom of that pre-existing hole. Then you'll see the coolant come on. The machine will kick on to that 88 surface feet or 27 meters a minute and begin this drilling application. Whenever you go in to do the drilling, it should be just drilling the hole. We shouldn't have any interruptions in that cut, no peck cycles or anything like that. And then whenever we're done with the cut, we're going to take it back to that 50 RPM for retraction so the tool doesn't whip when it gets into an unsupported state. So that's what we're going to do. Now the last thing before we get started here, I want to point out the speeds and feeds we're going to be running are reduced from the recommendations that are in the catalog. On the speed and feed page down in the lower corner, there is a reduction for 7 and 10 times D tools, and then another one for 12 and 15 times. The 7 to 10 times D are going to be reduced by 20%. 12 and 15 is going to be reduced by 30% because of those deep hole drilling applications. So the speed and feed that you see there, that 88 and 4 or 27 meters a minute, 0.1 millimeters per rev, takes that reduction into account. So Dave, if you're ready, let's go ahead and drill the 2-inch deep hole, or 50.8 millimeters. What you're going to notice is it's the same 787 diameter. Okay, so we're not going with a larger tool to a smaller tool for the deeper hole. It's both the same size because since it's a drill, it's going to drill inherently oversized, so it isn't going to pinch the drill when it comes in to do its cut. So we're drilling 20 millimeter diameter, 2 inches deep, 50.8 millimeters, running 88 surface feet a minute, 4 thou per rev, which is 27 meters a minute, 0.1 millimeters per revolution. Okay. Now, whenever he's done with this 2-inch cut, what we're going to do is we're going to gather up some of the chips because we want to make sure that the chip formation is something that's going to be acceptable for that longer deep hole drill whenever we come in with it. Because obviously, if I'm getting chip formation I'm not happy with the shorter drill, I'm going to be a lot less happy with it when I come in with the long tool, trying to push those not well-formed chips deeper out of the hole. So it just gives us the opportunity to gauge it and make sure that we're happy with the outcome. Okay, so we got about another 1/2 inch of cut to do before we're ready to take a look at those chips and see what's going on. Once again, remember this material is 718 Inconel. It's about 170 Bernal in hardness. So that's what we're machining here. And we've got really close to the end here. So once again, we're just going to gather up some of the chips, take a quick look at them, then we'll bring that long tool in and we'll show you the rest of the deep hole drilling guidelines. So Dave, let's just gather up a couple of chips just to show them. The long tool you got to load by hand, right? Okay. That's cool. All right, so I'm just going to show you what we got here. So here's the chips that we got. Running that 20 millimeter diameter, about 2 inches deep into the 718 Inconel, running at 88 surface feet a minute, 4 thou per rev, 27 meters a minute, 0.1 millimeters per rev, and you can see the chip formation's pretty good. So since we're okay with the chip formation there, we don't need to worry about making any adjustments to the speed and feed we're going to use with the longer tool. Because once again, if those chips weren't good for the shorter tool, when we come in with that longer tool, it's only going to get more problematic because now I got to shove the chip out of the hole further. And we want to make sure that that's okay. So now we're going to be using a 10 times D tool to drill the rest of this hole, going to a total depth of 5 inches. So remember, the first 2 inches are already drilled, so this tool is going to drill the last 3 inches of cut. But since we're using that 10 times D tool, we're going to use the deep hole drilling guidelines here. So you're going to see this longer tool coming in at a lower RPM, about 50 RPM, until it gets about an 1/8 inch or about 3 millimeters from the bottom of that pre-existing hole. And then it's going to go ahead and the coolant will kick on, you'll see the spindle come on, and it'll go ahead and drill the hole. Once again, speed and feed is going to be the same, 88 surface feet a minute, 4 thou per rev, which equates to 27 meters a minute or 0.1 millimeters per revolution. So Dave, if you're ready, let's go ahead and go. And you notice Dave had to load this tool by hand. It's because the length of this tool is a little too long for the tool changer that we have in this kit and mirror, and we want to make sure it doesn't get stuck, so we loaded it by hand. So you can see it's going in at 50 RPM until it gets down about 3 millimeters from the hole. You see the coolant comes on, and remember it's set at 600 PSI or 41.4 meters or 41.4 bar. And you can see the coolant's coming out quite well, and you heard that little bark when it first touched down. That's where it made contact. Now while it's running, the load should be relatively steady, which it's running a nice steady 9% right now, okay? You can see that the coolant's flowing out well, so that means we're not having any trouble with chip hacking. And you can listen to the sound. The sound is a nice, consistent sound. It's not varying in pitch, which tells us everything's going well. We're about 3 inches into the cut now, and it's still running at 8 or 9% on spindle load. Coolant's still flowing out rather nicely, so everything's going the way that we want it to. And we're now at about 3.5 inches depth of cut, still running at 8% spindle load. Coolant's still showing everything's working the way that it should. Okay, and remember, whenever it gets to the bottom of the cut, that's whenever the spindle is going to go back to 50 RPM for retraction, so that way it doesn't go into whip when we come out of the hole. We're now just about 4 inches into the cut, still running 9% spindle load. The coolant and the chips are still flowing out rather nicely, which is the way you want it to be. Because remember, whenever we're doing deep hole drilling, I got to get those chips out of the hole. And if I'm seeing evidence of poor chip evacuation, the way I'm going to know that is the pitch is going to change. The spindle load's going to start to become higher as it starts to catch chips. And you would see it based on the coolant flow, because you would see the coolant flow shut off and kind of spit the chips out. That's another indication that things aren't going well. And if you were here, you'd be able to feel the floor shake if that were the case. Okay, we are just about done, still at 9%. We're going to go back to that 50 RPM rotation on the way out, so the tool doesn't go into whip on the way out of the hole. And once we get the tool out of the way, we'll gather up some of those chips just to show them to you. They should look very similar, if not exact, to what we saw with that shorter drill whenever we ran it. And then we'll try to take this plate out so you can take a look at what the quality of the hole was as it was drilled. So let me grab a napkin here real quick. We'll just gather up a handful of chips here and show those to you. And the chips actually look quite good, which is the way you want them to be. Okay. Thank you, sir. That's good. Yeah, since these aren't magnetic, it's a little hard. We got to wait and pick them up by hand, which takes a little bit of time. So you can see, here's the chip form that we got. Now comparing that to, let me grab some of them that we got from before, if I can get my fingers around them. Okay, so let me find it here. Okay, so this is what we got with the short drill. This is what we got with the long drill. So obviously the chip form is basically the same as what we got between the two. And remember, that was running at 88 surface feet, 4 thou per rev, which equates to 27 meters a minute, or 0.1 millimeters per revolution. So once Dave gets that cleaned out, we'll kind of hold it up under the camera here so you can see the quality of the hole, and we'll just kind of put a nice bow on this and see where we go from here. Okay, so here we go. Once again, 718 Inconel, about 175 Bernal in hardness. Okay, now remember, this is not bored, this is only a drilled hole. That's why you see a difference there. The quality of the finish, I would say, is probably in the 150-ish range, maybe a little bit higher than that, but it's a decent drilled hole quality hole. Okay, and remember, this is a 5-inch deep hole. We did not drill all the way through, as you can see there. So looking at it, we drilled 5 inches deep with the TA Pro M geometry. Got a pretty decent finish. Feeling it, there's no like demarcation line where we went from the shorter tool to the longer tool, because remember, you heard that little bit of a noise once it first started to cut, which is absolutely normal in the way it's supposed to work. So those are the demos that we have for you today. I want to thank you for taking the time to watch our little video presentation here, and hopefully you had the opportunity to learn something about how Allied's products work in exotic materials like titanium and high temp alloys. Once again, my name is Rob Brown. I'm the engineering trainer here at Allied, and thank you for your time. See ya.